Hi everyone. Welcome to the final step of the MEDomicsLab testing phase, which is the challenge. This video will be different from the others as you'll need to create a model yourself. We'll guide you through the rules of this challenge, how to troubleshoot if you encounter issues with the application server, where to find useful information to understand what you can build with the learning module, and how to optimize your model. Before diving into this challenge, I strongly recommend consulting the documentation of the learning module on our GitBook, as you'll need to navigate it on your own for this step. At the beginning of this step, you should have, at least, a learning folder in your data directory containing the 2 new learning CSV files and the list of all patients present in this learning set. This new learning set corresponds to our previous learning and holdout set merged together, composed of 200 patients. We recommend starting this step in a new, clean workspace to avoid confusion between the different datasets used during the testing phase. The objective of this step, as explained in the GitBook, is to generate the best model you can using the learning set and send us this model, which will be a .medmodel file. We have already seen how to generate a .medmodel file in step 6 of the testing phase, but we will provide a quick reminder at the end of this video. There are a few rules to follow when creating your model. Firstly, your model must only consider the data we gave you for this step 8. Secondly, you are permitted to utilize modules other than the learning module. You can utilize the exploratory module to analyze the provided data and certain tools within the input module. Additionally, you have the option to use the evaluation and application modules if desired. Let's outline what you are permitted or not permitted to do with the input module for the challenge. You can utilize the merge tool only to generate a holdout set, similar to what was done at the end of step 3. This involves creating the holdout set based on the patient list and merging the learning and holdout patients across the various time point CSV files. However, we request that you refrain from merging the time point CSV files together. You are not permitted to utilize the grouping/tagging tool as it alters the column names of your datasets during model creation. Additionally, modifying the column names of your dataset is also prohibited. You are permitted to use the simple cleaning tool. You are permitted to use the holdout set creation tool, and we recommend following the procedure we used in step 3 by generating the holdout set based on the patient list and subsequently merging the learning and holdout patients with the time point CSV files if you wish to create a holdout set. You are permitted to use the subset creation tool. You are permitted to use the delete columns tool, but you have to keep the subject_ID and target columns in your datasets. You are not permitted to use the transform columns tool. In the feature reduction tool, you are not permitted to utilize the PCA tool. However, you can utilize the Spearman tool. If you opt for Spearman, ensure to retain the subject_ID and target columns by enabling the first 2 options in the dataset options section. And finally, you are prohibited from using the MEDprofiles tool. Once you've finished manipulating your dataset and you're ready to enter the learning module, ensure that your learning datasets are located in a folder named Learning. Otherwise, you won't be able to access them in the learning module. The CSV files must also be named with the prefix T__, for example, T1_. Otherwise, there will be some problems in the learning module. Additionally, if you've created a holdout set that you plan to use in the evaluation module, ensure that it is stored in a folder named Holdout with the same prefix as before. When you will conduct experiments in order to find the best possible model, you may encounter this type of error. You can attempt to rerun the experiment, but the error will persist. If you open the Settings tab by clicking on the bottom left icon, you'll notice that the server is disconnected, indicated by the server status line. All you need to do here is to restart the server. For this, you don't need to relaunch the app. You simply have to click on the Start Server button. To proceed, the Conda environment path must be set. It should be the case, but if it's not, here are the paths you must find depending on your operating system. Next, click on the Start Server button. Now, if you attempt to relaunch the experiment, it should work. As you create your model, you'll likely need information about what you can do with the learning module. The first place to look for documentation is our GitBook. We've gathered all the information you may need about our module there. Let's explore this documentation together. At the top of the page, we provide all the relevant links to the Picaret documentation since our learning module is based on this library. Afterwards, you'll find the link to our tutorial videos for the learning module, followed by instructions on how to create a scene and an overview of the module. One of the most interesting parts for the challenge will be here, where we describe each node independently and link them to the corresponding element in the Picaret documentation. For example, if we take the dataset node, we explain that it is associated with the options of the Picaret setup function that are not related to data cleaning. So, if you click on the link, you will have access to the description of the Picaret setup function and its options that you can retrieve in our learning module. Let's quickly review the documentation of the Optimize node, which we chose to implement as a subflow where each option of Picaret is a node. Each node has a dedicated section in the documentation, featuring a description, a basic example of usage, and various options that you can configure to achieve insightful outcomes. Even if you're not going to write any code, this can help you grasp what the node accomplishes and how you can enhance the results obtained. In our GitBook, we provide you with a section dedicated to the Optimize node and how to use it, along with a link to the complete documentation of each node comprising its subflow. You can find additional explanations in our GitBook regarding the various interactions available in the learning module, along with examples of use and guidance on understanding the pipelines. For those interested in the internal flow of Picaret, such as how the dataset is split into train and test, what scores are displayed in the compare models, train models, and analyze node, we conducted research to understand Picaret's processes and documented it in the What Picaret Does section. Let's now explore the Picaret GitBook, which is one of the links you can find at the top of the page. There are several interesting sections in the Picaret GitBook that will assist you in constructing pipelines for your model. One of the sections that is interesting to consult is the Quick Start section. It is divided into several parts, but as we are dealing with a classification problem, you can simply consult the classification part. This section explains the basic functionalities of the module. The examples are shown in code, but the same principles apply to our nodes. Another interesting section is the Data Pre-Processing section, which explains everything you can do while initializing a Picaret experiment through the setup function of Picaret. This function is divided between our dataset and clean nodes. You can also explore the Functions section, which provides a list of all the Picaret functions along with their descriptions. Some functions you may find here are not yet implemented in our app, such as the Analyze functions, as we have only incorporated the Plot Model function in this node, and the Functions from the Others tab. The Optimize node takes a train model as input and returns an optimized train model. In fact, it should be placed immediately after a compare models, train model, or load model node. When you click on the Optimize node, a new subflow opens with nodes related to the Optimize node. In this subflow, you already have two nodes present in the scene, start and end. These nodes represent the input and output of the Optimize node in the full pipeline. The pipeline you create in the Optimize scene must start at the Start node and end at the End node. When the Start and End nodes are connected, they turn green. Let's go through an example while building a pipeline with the Tune Model node. Here, I take the node and place it on each side of the Start and End zones. Once both are green, it means that the nodes are connected. This pipeline acts the same as if we only placed the Tune Model node in the position of the Optimize node in the complete pipeline. Since there are many options to optimize a model, we choose to group them in this Optimize subflow for clarity. As you may have noticed if you read the documentation of the Optimize node, some of the available nodes take multiple models as input and return one model as output. These nodes are blend models and stack models. If you wish to use one of these two nodes, you may pass multiple models to the input of the Optimize node. For now, the only way to pass multiple models to the Optimize node is by using the Compare Models node and setting the in-select parameter to more than one. The output of the Compare Models node will be the in-best models. You can compare the results of the Compare Models node and the Blend Models node to see if the Blend Models node is interesting to use in your case. To conclude this video, we will construct a pipeline together that you can choose to use, or not, to assist you in finding the best possible model for our problem. Additionally, I'll provide you with some advice on the tests you can conduct and which options are useful to configure in the Learning module. Let's begin by creating a new scene. Click on the Learning module icon, then click on the Create Scene button and enter the name you prefer. Finally, press Create. Open your scene file, located under your New Scene folder within the Experiment folder. Every pipeline must start with a dataset node, so let's add one to the scene. I begin by selecting the T1 and T2 datasets. Then, I'm selecting all the tags and variables. However, when conducting your experiments, you'll need to select only specific tags and variables to achieve better results. As we've seen in previous steps, having too many columns can hinder model training. Next, let's enable two useful options in our dataset node, Index and Session ID. The Index option specifies to the module that our subject ID column is an identifier column and not a feature to train on. The Session ID parameter acts as a seed and is here to ensure reproducibility of our experiments. It ensures that the split between the train and test sets remains consistent across different runs, as well as any treatments in the pipelines based on random numbers. This consistency allows us to compare our results based on the models we create rather than random splits that may affect model performance. Let's enter subject_ID as the index and 123, for example, as the session ID. Next, let's add a Compare Models node, which will train all the available models on our dataset and return the one with the best results. However, here we are going to enable the in-select option, which will allow us to return the specified number of best models. Let's enter 3 as the number of models to return. This will be really useful to help us see if some models perform better after an optimization step that we will add right after. Let's now add an Optimize node to our pipeline. Click on the node to open the subflow related to it. Here, we are only going to use the Tune Model node, which will search for the best hyperparameters for the models using the scikit-learn randomized search CV function and the Picaret default tuning grid for the models passed, which you can find on their GitHub. We are now going to enable the Choose Better option of the Tune Model node and set it to True. This will allow us to keep the best model by comparing the Tune model with the original model, because in some cases, the result of the original model is better than the result of the Tune model. Let's return to our scene. We'll add an Analyze node and a Save Model node to the scene. The Analyze node will display the results of your models on the test set defined by Picaret and help you determine which model seems better. The Save Model node will save your models in the Models folder within your scene folder as .medmodel files that you will then be able to send us. By default, the Analyze node displays the AUC plot of the past models. However, as we've seen in Step 6, not all models have an AUC plot available. So we are going to display another plot by enabling the plot option and entering error as the plot type. This will display the proportion of 1s and 0s predicted depending on the true 1s and 0s target for each model passed. At this step, don't forget to save your scene. Let's now run the experiment. Once the results have been generated, you can observe that your 3 models have been saved in the Models folder of your scene. These are the 3 best models from the Compare Models node, which have been tuned if this improved their performance. If you open one of the .medmodel files, you will observe that the models take into account a lot of columns. You can also observe the results of your pipeline and draw conclusions on your own. Here, we see that the 3 best models based on accuracy are the random forest classifier, the k-nearest neighbors classifier, and the ridge classifier. Additionally, the Tune model has improved the accuracy of the KNN and ridge, but decreased the accuracy of the random forest classifier. If you observe the analyzed node, it seems that the k-nearest neighbors classifier is the best model among the 3 selected, but the performances are not particularly good. Indeed, as mentioned earlier, if you aim to achieve better results, you should select only a few tags and columns to assist your models in training more effectively. You can utilize this pipeline and enhance it by experimenting with options, adding or removing nodes, or creating your own pipeline. The only requirement is to solely consider time points 1 and 2 from this step 8 data and include a save model node at the end of your pipeline so that you can submit your best model to us. Well, have fun creating your best model. Don't forget to send it by email following the rules mentioned on the GitBook page of this step.